Hello all, welcome back. In the previous few lectures we were discussing about the estimation of evaporation. Initially we have discussed the experimental method of estimation of evaporation, that is measurement of evaporation by using experimental techniques. After that we have started with the analytical methods which are used for the estimation of evaporation. In that first method we have already seen in the previous lecture, that is the energy balance method. In that what we have done, we have made use of the continuity or the mass balance equation along with the energy conservation equation for deriving the expression for rate of evaporation. So, in that particular equation both the energy conservation and the mass balance together considered. The main factor which we have considered in the energy balance method was the heat energy, that is heat energy provided by the sun is absorbed by the water in the water body. That was the predominant factor which we have considered while deriving the energy balance equation. Today we are going to see aerodynamic method. In aerodynamic method, what extra factors which we are considering other than heat energy, let us see one by one in today's lecture. So, the important factors affecting the evaporation rate from an open water surface, which we have seen supply of heat energy from the sun and ability to transport vapor away from the surface. Evaporation is the process by which the water is converted to water vapor. So, this water vapor will be moved from the water body to the atmosphere. So, this has to be removed continuously from that particular location. If it is there only, again and again addition of water vapor will not be possible. It is possible only up to the saturation point. Beyond that it is not possible. So, continuous transport of this water vapor from the above the water body is required. So, the two important factors which are influencing evaporation are the heat energy and the vapor transport away from the water body. So, now here in this aerodynamic method we will be incorporating the transport of vapor. Vapor transport will be considered. In the previous method we have been using heat energy, that is the emphasis was given to heat energy, but heat radiation, but in this case we will be considering the vapor transport. So, the transport rate is governed by humidity gradient in the atmosphere and wind speed. That is, humidity gradient means we are having a certain vapor pressure corresponding to the given temperature and there is a maximum capacity for the air to hold water vapor. So, that will be at that point the vapor pressure will be saturation vapor pressure. So, from the existing vapor pressure to saturation vapor pressure, that much can be added, that much pressure can be increased by the extra addition of the water vapor. So, there is a deficit in the humidity or the water vapor. So, the humidity gradient near the water surface is very important. Second factor is that more and more water vapor is added to the atmosphere. This thing should be transported by means of wind action. So, how this transport is taking place? The wind will be carrying away this water vapor which is added to the atmosphere. So, once the water vapor is getting transported away from the water body, more and more water vapor will be added to that particular location. So, that fact, in that case wind is playing the predominant role. So, here in this method of aerodynamic approach, we are making use of the humidity gradient and also the wind velocity which is prevailing at that particular location. So, these two processes can be analyzed by coupling the equations for mass transport and also momentum transport. That is, these mass transport and momentum transport related to the water vapor we are going to consider, and these two processes such as the humidity gradient and wind velocity gradient will be considered by coupling the equations related to mass transport and momentum transport, mass and momentum transport related to the water vapor. For this also what we are going to do, we are going to consider a control volume. So, control volume within the water body we will be considering. So, we will be considering a control volume just above the water body. So, let this be the water surface and consider a horizontal unit area located at a height of z above the water surface. So, we will be considering the vapor movement in the upward direction, that is we are considering the z direction in the upward direction. So, this is our control volume and heat energy is absorbed by the water. That net radiation is denoted by Rn and evaporation in the upward direction is taking place from the water body. And now, our interest is to find out the vapor flux m dot v passing upward by convection. The transport process which is responsible for the vapor transport is the process termed as convection. Different transport mechanisms are there. So, out of that we will be making use of the principle of convection here in the vapor transport. And air flow will be, once the water vapor is added to the atmosphere, due to wind action it will be removed from that location or it will be transported from one location to another. So, the airflow direction is marked in this way. Now, we know already as the elevation is increasing, wind velocity is increasing. That relationship is shown in this particular figure as the value of z is increasing, wind velocity is also increasing. Then coming to the temperature, as the elevation is increasing, we know the temperature is decreasing, right, that we have already seen. And then coming to specific humidity, as the elevation is increasing, specific humidity is also decreasing, because we know altitude is high means it is far away from the water body and the moisture which is present in the atmosphere will be less compared to the location which is near to the water surface. So, as the altitude is increasing, the specific humidity will be reduced, decreasing. So, these are the principles which we are supposed to know while deriving this equation. So, two different transport mechanisms I am explaining here, and the mechanism which we will be utilizing here or the vapor transport is taking place is due to convection. So, two different transport processes are convection and conduction. So, in the case of convection, transport occurs through the action of turbulent eddies. So, turbulent eddies will be present, the transport of water vapor will be taking place due to the action of turbulent eddies, or the mass movement of the elements of fluid with different velocities. The fluid elements mass movement will be taking place, but in the case of conduction it is due to the movement of individual molecules. That is, conduction process is taking place through the movement of individual molecules, but in the case of convection it is not due to movement of individual molecules, it is due to the mass movement of elements of fluid. So, convection is possible, in the case of convection is possible if we are having flowing fluid, it requires a flowing fluid, but in the case of conduction it does not require a flowing fluid. So, the difference between convection and conduction you are supposed to know, and the process or the transport process which we are going to make use in this particular derivation is the convection process. And in the aerodynamic method we have already mentioned the factors considered are the humidity gradient. So, what is the notation used for humidity? That is QV. So, when it comes to humidity gradient, as the two different altitudes are there, what is the difference in humidity with respect to difference in altitude? So, that can be represented by dQV divided by dZ. And second one is the wind velocity gradient. that is represented by du by dz. U is the notation used for wind velocity and the du value corresponding to du by dz is considered as the wind velocity gradient. Why we are taking these two gradients? Because these are the two factors, predominant factors which are responsible for evaporation, and these two are considered in the method known as aerodynamic method. Now coming to the vapor flux notation is mv dot that we have already used. So, the vapor flux mv dot passing upward by convection. What we are doing, we are considering we have seen the control volume. Above the water surface, we will be considering a plane parallel to the water body. Through that plane, how much vapor transport is taking place due to the process termed as convection. So, that can be written as, that is, mass flux m dot v is actually proportional to the specific humidity gradient, that is humidity gradient dqv by dz. dqv by dz is our humidity gradient, and humidity gradient, what is it representing? The difference in the humidity at two different altitudes, right. So, because why we are considering that, we can add more and more water vapor only if it has not reached the saturation vapor pressure. So, we can add up to, or the evaporation process can add a vapor, add an amount of vapor into the atmosphere until it reaches the saturation condition. So, that is why this humidity gradient is coming into picture. So, the vapor flux mv dot is represented by this particular expression, that is, it is proportional to how much gradient is there corresponding to specific humidity. mv dot is directly proportional to dqv by dz. Next is the momentum flux. Momentum flux is represented by the notation tau. Tau, momentum flux which is taking place in the upward direction, again due to convection. The transport process which we are explaining here is by means of convection. So, vapor flux passing upward by convection we have written, and in the similar way momentum flux is also taking place due to convection, that is written by tau is directly proportional to du by dz. Mass flux is proportional to humidity gradient, and the momentum flux, how much momentum flux is taking place, that depends upon the wind velocity. That is why it is proportional to du by dz, wind velocity gradient. We know already what is getting evaporated due to the heat energy and the humidity gradient in the atmosphere, and due to the action of wind, the transport of water vapor is taking place. So, net transport of water vapor from the water body is taking place due to wind action. So, three important factors: heat energy, then comes the humidity gradient and wind velocity gradient. Heat energy we have considered in the case of energy balance equation. In the case of aerodynamic equation, we are considering the wind velocity gradient and the humidity gradient. So, the vapor flux passing upward by convection can be written as mv dot is equal to minus rho a kw dqv by dz. What we have written in the previous slide, mv dot is directly proportional to dqv by dz. Vapor flux is directly proportional to, or the mass transport is directly proportional to humidity gradient, and that proportionality is removed by means of the constant. So, the expression has changed the form. Any process, any expression related to convection, different actions will be taking place, the equation will be having this form. So, here we are having mv dot is equal to minus rho a kw dqv by dz. So, here rho a is the density of air, kw is the vapor eddy diffusivity. This is a constant depending on the environment. Here we will be considering kw to be constant. Then we know dqv by dz, that is the specific humidity gradient. Qv is the specific humidity. In the similar way, momentum flux tau upward through the horizontal plane can also be written, that is tau is equal to the process is same, that is the convection process. So, the expression, you compare these two expressions, that is, one is related to vapor flux, mass transport, and the other one is related to momentum flux. Here tau is equal to rho a km du by dz. So, here we are having rho a, density of air. U is the wind velocity at height set. Du by dz we are taking, in the previous case dqv by dz, specific humidity qv is considered. When it comes to momentum transport, it is related to wind velocity, that is the wind velocity u at an height of z is considered, and rho a is, km is the momentum diffusivity or eddy diffusivity. Momentum diffusivity or eddy diffusivity is the constant of proportionality we are considering, and rho a is the density of air. Now, what we are going to do? We are going to consider the two horizontal planes. So, as the altitude increases, that was our gradient we were considering, that is two heights, difference in the specific humidity at two different altitudes. In the similar way, difference in wind velocity at two different altitudes. So, we need to consider two planes at heights z1 and z2. So, in control volume we are considering, evaporation is taking place, we are having the airflow. Airflow velocity is the wind velocity, which we are considering as, denoting as u. And we are considering two planes z1 and z2. z1 and z2 both are considered to be very close to each other, because we need to make an assumption that the variation in specific humidity or in the wind velocity is linear. That is why the gap between these two planes which we are considering should be minimal. So, dqv by dz can be written as qv2 minus qv1 divided by z2 minus z1. And then coming to velocity gradient, wind velocity gradient, it can be written as u2 minus u1 divided by z2 minus z1. So, why we are able to write this expression in the difference form? Because we are assuming that the variability or the variation of the specific humidity or the wind velocity between these two planes z1 and z2 are varying linearly, because the gap between these two planes are very less. Now, what we are going to do? We are going to divide the two equation which is representing the vapor transport, mass transport and mass flux and the momentum flux, mv dot and tau. Mv dot is the mass flux and tau is representing the momentum flux. So, what we are going to do? We are going to divide these two equations, mv dot divided by tau. So, right hand side negative sign is there, rho a kw dqv by dz divided by rho a km du by dz. So, mv dot divided by tau is equal to minus rho a gets cancelled, we can cancel these things, and kw by km, and what we will be doing for dqv by dz and du by dz, we will write the difference equation, that is z2 minus z1 will be getting cancelled, and our expression will be taking the form qv2 minus qv1 divided by u2 minus u1, that is mass transport divided by momentum transport. mv dot divided by tau is given by minus kw by km qv2 minus qv1 divided by u2 minus u1, or m dot v is given by tau, we are taking towards the right hand side, tau multiplied by kw divided by km qv1 minus qv2 divided by u2 minus u1. Now, next step is to estimate the value corresponding to momentum flux tau. Momentum flux is related to wind velocity gradient, that you have to keep in your mind, and using the concept of wind velocity in the boundary layer. In fluid mechanics, you might have studied the boundary layer concepts. Here we are going to make use of that concept related to wind velocity. So, we are going to make use of the concept of wind velocity in the boundary layer almost up to 50 meters in the atmosphere. So, what is the expression corresponding to velocity distribution in the boundary layer theory? That is given by u by u star is equal to 1 by k ln z divided by z naught. This is the logarithmic distribution of velocity, logarithmic profile law of velocity at the boundary. So, if you go through the boundary layer theory which you have studied in fluid mechanics, this will be, you will be reminded of this particular equation at the boundary. So, this particular equation we will be making use here in the case of estimation of momentum flux. So, here we are having the term shear velocity u star. Shear velocity, how can we get the value or the expression corresponding to shear velocity? It is given by under root of tau divided by rho a. So, what is tau? Tau is nothing but our momentum flux. So, u star is given by under root of tau divided by rho a. Do not worry about these expressions, these are taken from the boundary layer theory. So, that we are applying here for the wind velocity. So, k which we have used in the previous slide is the von Karman constant. This value is taken to be approximately 0.4 and z naught is the roughness height of the surface. Now, use these equations for two planes, plane 1 and plane 2 which we are considered, that is we have considered two planes at z1 and z2, right. So, what we are going to do? We are going to write the velocity distribution expression for two different planes. That is our velocity distribution equation is u by u star equal to 1 by k ln z by z naught. Here this k is the von Karman constant and z and z naught. Z is the level which we are considering, z naught is the roughness height of the particular surface. We will be write the equation for two different altitudes, that is u1 is equal to u star divided by k ln z in that particular case is z1 divided by z naught and u2 is u star divided by k ln z2 divided by z naught. After that what we are going to do? We are going to subtract these two equations, subtract one from the other. So, u2 minus u1 we are going to write, these u star by k is coming in both the equations, that can be taken as common. So, u star by k multiplied by ln z2 divided by z naught minus ln z1 divided by z naught. We got the equation like this. So, we are having the logarithmic term within the bracket that can be rearranged. So, it can be written as u star by k ln z2 by z1. Z naught is getting cancelled. So, the expression for wind velocity, difference in wind velocity at section 2 and section 1, that is u2 minus u1 can be written as u star divided by k ln z2 by z1. Why we are doing all this exercise? We need to get an expression corresponding to our momentum flux. So, how can we relate these things? Our momentum flux term is here in the expression for shear velocity. Shear velocity u star is given by under root of tau divided by rho a. Let us see how can it be obtained, how we can get the expression for momentum flux. Here we are having the shear velocity. Now, if from the previous expression we are going to, that is from this expression we are going to get the expression for shear velocity u star. U star is equal to, we are rearranging the equation, u star is equal to k u2 minus u1 divided by ln z2 by z1. And then we will substitute the expression containing momentum flux here, and from that we can find out the expression for momentum flux. So, everything converted in terms of wind velocity. Shear velocity is given by this particular expression under root of tau divided by rho a. So, that we will be substituting here. So, u star is taken as under root of tau divided by rho a is equal to k u2 minus u1 divided by ln z2 divided by z1. Momentum flux tau is within the root. So, we need to square the expression, and after that rearranging the terms we can get the expression corresponding to momentum flux tau. So, we have squared the expression, all the entire right hand side will be having the power 2 and rho a, this left hand side will be tau by rho a. So, tau by rho a is equal to square of the right hand term. So, from that we will be finding out the expression for tau. It will be coming out like this, rho a multiplied by k u2 minus u1 divided by ln z2 by z1 all square. So, this is the equation corresponding to momentum flux tau. Now, what we are going to do, we are having the equation corresponding to mv, that is we have divided the mass flux and the momentum flux. mv divided by tau we have done initially and mv in terms of tau we have written there. Now, we are having the expression corresponding to momentum flux tau from the velocity distribution law near the boundary layer. So, we will do the substitution for tau, that is this is the equation for mv dot, that is our mass flux. So, here for tau we will be substituting the expression which we got in the previous slide. So, we got a lengthy expression for mass transport. mv dot is given by rho a multiplied by this entire term. This entire term is representing our momentum flux, that is tau. That is substituted over here, multiplied by kW divided by km multiplied by qv1 minus qv2 divided by u2 minus u1. This equation can be rearranged. Somewhat we can make some rearrangements because we are having u2 minus u1 here and also u2 minus u1 here. So, that can be cancelled. So, it will be rho a k square u2 minus u1 all square divided by ln z2 by z1 all square kW divided by km qv1 minus qv2 divided by u2 minus u1. So, this u2 minus u1 and in the numerator we are having u2 minus u1 all square. So, that gets cancelled and the final expression takes this form, kW k square rho a qv1 minus qv2 u2 minus u1 divided by km ln z2 by z1 all square. When you derive step by step you will get this equation. It will be slightly difficult to remember, but step by step derivation will be leading you to this final expression. So, this final expression is for the vapor flux taken away due to wind velocity. That is, we are having the process of evaporation taking place near the surface of water body. Water vapor is getting added to the atmosphere, that has been transported by means of wind velocity. So, the process which is taking place, how much vapor transport or the mass flux is taking place due to the action of wind velocity can be obtained by using this equation corresponding to mv dot. This is the well known Thornthwaite-Boltzmann equation. This equation is very commonly used in the case of evaporation. So, this equation is based on the aerodynamic method. The equation which is derived based on the aerodynamic method is termed as Thornthwaite-Boltzmann equation. Now, we are having different terms, right? QV, QV1 and QV2, that is the specific humidity at level 1, Z1 and Z2. And different Ks are there, these things have to be measured or estimated. Okay, specific humidity, wind velocity can be measured, specific humidity can be calculated. We are having the expression corresponding to specific humidity in the water vapor dynamics we have studied. So, those equations we will be utilizing here and we can calculate these values or the values which are measured such as wind velocity at different levels, or it can also be calculated by using different formula relationships. So, those equations will be utilized and we can finally calculate how much is the vapor flux taking place at that particular location. Now, that equation you have seen slightly lengthy and it is difficult to remember. So, what we are going to do, we are going to simplify that particular equation. The simplification of Thornthwaite-Boltzmann equation can be done by assuming Kw by Km. Kw and Km are constants, constant of proportionality, and that can be taken to be unity. Then what we are doing? We are having the wind velocity at two levels Z1 and Z2. What we are going to assume, we can consider Z1 very close to the water body, on the surface of the water body. So, Z1 is considered as Z0 and wind velocity close to the ground is 0 due to no slip condition. That is, water surface is not moving. Water body, in the water body, water surface is not having any movement, not having any velocity. So, based on the no slip condition, we can assume that the air which is moving near to that surface also will be having the velocity as that of the water surface. What is the velocity of the water surface? Since it is not moving, since it is a water body like a lake or which is not moving, then we can assume the velocity of the water surface to be 0. So, that can be considered. The wind velocity at section 1 can be considered to be 0, because we are assuming that section 1 is at the water surface. So, section 1 we are considering at the water surface. So, there the air will be saturated, because the more and more water vapor is added continuously. So, the air will be saturated near the water surface. So, the air is saturated with moisture at Z1 equal to Z0, very close to the water body. All these are simplifications. We need to make the simple form of Thornthwaite-Holtzman equation. So, air is saturated. This assumption is leading to us, giving us that from the temperature close to the water surface, the saturation vapor pressure can be calculated and QV1 can be calculated, that is surface Z1 is equal to Z2. So, corresponding to that temperature, we can calculate the saturation vapor pressure and also specific humidity. What is the expression for specific humidity? It is given by QV is equal to 0.622 E by P. E is the vapor pressure, P is the atmospheric pressure. These can be measured. Now, coming to relative humidity, we know it is given by EA divided by ES. These equations we have already seen. So, EA can be calculated by using the equation EA is equal to ES multiplied by relative humidity. Now, QV1 is given by 0.622 E1 by P Z naught. P Z naught is the level pressure at the water surface. It is given by 0.622 ES divided by P Z naught. With the assumption near the water body, we are taking the value Z1 equal to Z0. So, at that location just above the water body, the air will be fully saturated and we can take the vapor pressure to be saturation vapor pressure. So, QV1 expression is simplified. So, QV2 is corresponding to 0.622 E2 divided by PZ2. Put all these assumptions in equation for vapor transport. So, this is our vapor transport equation. We have assumed Kw by Km is equal to 1, and then we are having the expressions for QV1, QV2, so that we can substitute in this equation. So, the equation will be taking the form mv dot is equal to QV1 and QV2, we are having the expression in terms of ES and E2. So, when it is QV1 minus QV2 is calculated, it will be coming out to be 0.622 ES minus QV2 minus QV1 will be 0.622 ES minus E2 divided by A atmospheric pressure. So, that we are considering PZ0 and PZ2 as P. So, it will be 0.622 K square, this K square is coming from here, rho A, instead of QV1 minus QV2, we got the expression 0.622 ES minus EA divided by P. So, you may get confused where this PZ2 and PZ0 have gone. It has assumed to be the atmospheric pressure. So, that is represented by P, which is not varying, that variation we are not considering. So, the expression takes the form 0.622 K square rho A ES minus EA divided by P multiplied by U2 divided by ln Z2 by Z1 all square. Why U2? U2 minus U1. In the term U2 minus U1, U1 we have considered to be equal to 0 based on the no slip condition. the surface layer of air which is close to the water surface will be having the same velocity as that of the water surface, that is equal to 0. So, this is the simplified form of the Thornthwaite-Holtzman equation. Now, we know continuity equation for evaporation process. This we have seen, mass balance equation we have seen in the previous class. It is given by mv dot is equal to rho w EA multiplied by area from which the evaporation is taking place. That area we are considering unity, A is equal to 1. So, mv dot is given by rho w EA. Why do we want to make use of this equation, continuity equation here? Because our aim is to find out the evaporation rate that is contained in the mass conservation equation. So, mv dot is given by rho w EA. So, that we will be substituting here. EA is the rate of evaporation from water body based on aerodynamic method, and that we will be substituting here. For this vapor transport we will be substituting rho w EA, and from this we will calculate the expression for EA. So, rho w EA is given by this, EA is equal to 0.622 rho A divided by this rho W is coming to the denominator. So, EA is equal to 0.622 rho A divided by rho W K square ES minus EA divided by P U2 divided by ln Z2 divided by Z1 all square. So, EA is given by, so we can write EA, this expression as such, entire expression we are considering, and we are simplifying it in such a way that EA is equal to B multiplied by ES minus EA. What is ES minus EA? It is the saturation vapor pressure minus the vapor pressure corresponding to that particular temperature, deficit in the vapor pressure. So, EA is given by B multiplied by ES minus EA. So, we are keeping only these terms ES minus EA here, and all other terms combined together under the term B. So, B is written, all terms combined together we are substituting as B for getting a simplified equation. So, EA is written as B multiplied by ES minus EA. This equation together known as aerodynamic model for evaporation. So, based on aerodynamic method, aerodynamic equation what we have considered? We have considered the specific humidity and the wind velocity gradient, and we have written the mass flux and the momentum flux. Mass flux and momentum flux expressions for the process, transport process which we have considered is convection. So, for a convection process how the equation will be looking like, and based on that particular equation we have used the equation corresponding to mass transport and momentum transport and divided each other, and we have made use of the velocity distribution expression near the boundary layer for getting the expression for wind velocity, and by making use of all these theories we have finally calculated the evaporation. How did we get the evaporation? By incorporating the continuity equation. So, here we have made use of the continuity or the mass balance equation, specific humidity gradient and also wind velocity gradient. So, by making use of all these principles finally we got the simplified equation for calculating the evaporation rate based on aerodynamic method. That is why we are having EA. Based on heat energy, heat radiation, it was represented ER in the previous lecture, and today we are representing EA. EA is given by B multiplied by ES minus EA. But B is a complicated expression, but final expression we can tell EA is equal to B multiplied by deficit in vapor pressure. This is the aerodynamic model for the calculation of evaporation. So, the reference textbooks which I have utilized are these books, and the derivation is mainly I have taken from Applied Hydrology by Venti, Chow and others. So, here I am winding up this lecture. Thank you.